So hello everyone. It's well, it's 2 o'clock. So we're still waiting for I guess for more attendees to join the session. But in the meantime, we are of course in the parallel session 4 on improving integration and efficiency, and I'll go through some housekeeping in a minute or so, and also just present very briefly the speakers. And then we'll start with the first speaker in the agenda around 2:05. So just wait a couple of minutes more to see if we have a few more attendees joining, as people are joining now. So yeah, and then we'll start. So just for you joining in just now, so this is parallel session 4 on improving integration and efficiency. We're just waiting for a couple more minutes to see if we have a few more attendees joining in as people are just joining the session. And then I'll go through some initial housekeeping, which will take me a couple of minutes or less, and then just presenting very generally the speakers, and then we'll start the sessions really shortly. So the presentations really shortly. Okay, we'll start, and then I guess people will join in as the session progresses. So good afternoon. This is a parallel session for improving integration and efficiency. My name is Zenaida Morau, and I'm the chair of the session, and Marianne Zeringer is the co-chair. And we have, so we just have initially some housekeeping, and then we'll share just a very brief intro of the speakers and the presentations, and then we'll go on to the first presentation. So as to start off with some housekeeping, this session is being recorded. So if you do not want your name to appear in the video, you can change it by clicking to the right of your name. There's an option that says more, and if you click on more, you can then rename, and basically that's how you change your name. Then we will have the 5 presentations back to back, so we will not have questions in between, so for each presentation individually, but we will have all the questions at the end in a communal question and answers at the end, which we are aiming for 15 minutes. It might be shorter, it might be a little bit longer, depending on the time that we spend in the presentations. In order to pose your questions or to make any comments, you can raise your hand or use the chat. Of course, by raising your hand, this means basically mostly during the communal question and answers. During the rest of the time, you can use the chat. All of the speakers are aware that we have the chat, that they can directly interact with the attendees. And of course, you can pose the question directly in the chat section. You can actually direct it to a given person within this session. So if you're using the questions, let's say generally in the panel for everyone, please do not forget to identify the speaker so that we know whom this question is directed to. Also, please do remember to switch off camera and mute your mic. Of course, you can then switch them on if you want to pose a question during the communal question and answer session at the end. So just as a quick overview of the program we have today within the session. So we have 5 presentations. It's going to be a really interesting session because there's quite a bit of variety here in terms of the energy system, and of course in terms of different focus on local versus also centralized. We have some data focus on basically on integrating data, on basically also integrating different models and different systems as well. So it should be, I think it will be a really interesting session. So the first speaker is Sebastian from TU Wien. He'll be talking about heat density of centralized heat networks for Austria 2050 under a 1.5 climate target. That presentation will be followed by Jakobs from Aalborg University, who will be talking about integration across models, so converting primes results into energy plan. Then that session is going to be followed by Mark from Utrecht University and the Copernicus Institute with a very catchy title, so Apples with Apples and Pears with Pears, which talks about integration of data and of course databases from different energy models, which happens quite often when working with different models and soft linking and so on. Then we'll have in comparison between models. Then we'll have Marta from Aarhus University. She'll be talking about solar photovoltaics and basically how it's ready to power a sustainable future. This is going to be really exciting, I think, also because so many different countries are considering quite a bit of an expansion, of course, in renewable power, and both centralized and decentralized. So we'll be really looking forward to hearing from her. And we close with Dieter from Siemens, and he'll be talking about the integration of basically electricity and gas transport. So it'll be really nice to see this multi-vector integration and what they have been basically modeling and what results they've been having. So without further ado, I will ask Sebastian to, I'll stop sharing and ask Sebastian to share the presentation from his side. So just give me 1 second. Okay, Sebastian, go ahead. The floor is yours.
Thank you very much for the introduction. Now you should see my screen, right? But not in the presentation mode.
We can see it. Yep.
Okay, super.
Great. Yeah.
So thank you very much for joining this session. This is Sebastian speaker from today, Cloudy Vienna. So in the next couple of minutes, I will talk about, let's say, the role of centralized heat networks under the 1.5 climate target, focusing on an Austrian case study. In this project, so we use the downscaling techniques to, let's say, project and assess the heat densities of centralized heat networks. So first of all, I will start with, let's say, an overview of the current state of the European heating sector. First of all, it's important to say in this context that we have to think about the heating and the cooling sector together. And we see here, for example, the share is just 20%. So currently, just 20% of the heating and cooling sector is based on renewables, in average in all EU member states. Of course, and here, for example, the number for Austria, in some countries we have higher shares. For example, here in Austria, we have 34%. But of course, fossil fuels continue to dominate the provision, especially in the heating sector, but also in the cooling sector. So for example, just to give some representative numbers, we have 900,000 dwellings that are heated with natural gas, for example, in Austria, and more than 500,000 that are heated with oil. So these are the numbers for Austria in 2020. For example, just to give an idea what this would mean if we want to decarbonize this number of dwellings, which means that we have to retrofit 50,000 appliances per year, or more than 130 per day. So as we also heard in the introduction speeches today, we also have to think about, let's say, suboptimal solutions to decarbonize, for example, the heating sector, because we have to be fast facing this problem. So the options to decarbonize the heating sector can be summarized as follows. So we need need a massive expansion of different technologies. And here, for example, we name the centralized heating and cooling networks that give us the option to ensure a highly efficient usage of renewable heat sources, for example, biomass, waste, and hydrogen, and also to achieve, as I said, the significant retrofitting rates by high connection rates. And the third aspect is also very important. We need centralized heat networks to unburden the electricity sector because we expect high electrification rates in other sectors as well, for example, the transportation sector. So just to summarize the core objective of this work and this presentation, the core objective was to downscaling European decarbonization scenarios of the heating sector from the country level to the community or distribution grid level in 2050. In particular, we want to focus on the downscaling on the highly efficient use and local use of sustainable heat sources in centralized heat networks, for example, as co-firing from hydrogen in cogeneration plants. The third aspect of the core objective is to consider also the topography of district heating networks, because we know that the topography and the network topology of centralized heat networks is important if we talk about the economic viability of centralized heat networks. And the fifth point is that we took the results from European decarbonization scenarios. To be more specific here, we took the results from the Genesis mod, from the large numerical energy system mod Genesis mod, that generates, let's say, the portfolio on the country level, and we used these results in the year of 2050 to downscale, as I said, to the community and distribution grid level. Just a very short idea how we did this. We used 3 different downscaling techniques. The first one was a reference technique, which is often used in this regard, is called the proportional downscaling, using, for example, here, population as a proxy. But we developed 2, let's say, more sophisticated or more advanced techniques called here the sequential downscaling and the iterative downscaling. So for example, just to give an idea, the sequential downscaling is used to downscale from the country level to the NUTS-3 level, which means for Austria, for example, that we took 1 node and disaggregated to 35 different nodes. And the iterative downscaling is a technique that is used to downscale from these NUTS-3 regions to the community level, which means, for example, that we split these 35 different nodes to more than 2,000 different nodes for Austria, for example. The sequential downscaling uses population density as a criteria, and iterative downscaling is based on graph theory benchmarking of the network topology. So here, just a very quick idea of the sequential downscaling. As I said, we want to use the population density and the highly efficient use of heat sources in the downscaling techniques, which means in the end that we benchmark the heat sources according to their requirements for network infrastructure. And so, for example, heat source A here on the left-hand side is a technology that has high network infrastructure requirements, and this heat source is only downscaled to subregions that can provide the network infrastructure, which is indicated, as I said, by the population density. Heat source B has lower network infrastructure, which means in the end that it's downscaled to a higher number of subregions, which is indicated by the blue marked areas on the right-hand side. The main concept of the iterative downscaling, as I said, uses network topology and graph theory benchmarking. And here we developed a so-called clustering coefficient C, which means in the end benchmarks a specific subregions. So in the end, a high clustering coefficient means from a supply company perspective, this subregion can achieve, on the one hand, a high connection rate and also a high heat density. And both indicators are very important from a heat supply company perspective to supply and connect a specific subregion to a centralized heat network or not. So this is used in the iterative downscaling algorithm, taking into account the so-called clustering coefficient C, which is here illustrated on the two figures. Just to check the time. Okay, super. Yeah, as I said, we used the results from the large numerical energy system model Genesis mod, and we used 4 different decarbonization scenarios that are developed in the ongoing Horizon 2020 project Open Entrance. So we used the 4 different scenarios called here directed transition scenario, societal commitment, techno-friendly, and gradual development scenario. It is important to say, and this is also indicated in the figure on the bottom, that the numbers that are downscaled include efficiency measures and also a reduction of the total heat demand. So if I talk about the heat density and centralized heat networks in 2050, this a priori includes the efficiency measures that are necessary to reduce the heat demand significantly, which is here illustrated in the figure at the bottom. So just a very quick overview of the results, 4 different slides of the results. Here we can see the results on the country and also on the sub-region and on the community level. On the left-hand side, you see the composition and the shares of the different heat sources in 2050 in the 4 different decarbonization scenarios. You see, for example, high shares of biomass and also from different types of heat pumps, for example, air sourced and ground sourced. You see that specific technologies that require network infrastructure are only downscaled to the urban subregions. For example, here providing a high population density, which is used in this work as an indicator for the potential of network infrastructure. And you can see the estimates for the topology on the community level for the 4 different scenarios. And you can see, for example, that the techno-friendly scenario results in the smallest expansion of the centralized heat network, but in the gradual development, which is the less ambitious scenario under these 4 different scenarios, we need high shares of and a significant expansion of the centralized heat networks, for example, here in this highly populated area called South Viennese environs, which is in the south of Vienna. To give an overview of the results here, you can see that we indicated that we generated in the end 8 different subregions that provide the possibility for centralized heat networks in Austria in 2050. Here you can see the heat demand that is supplied by the networks, but it's important to note that we also saw in the results that it's important to go deeper into the spatial resolution, which is indicated here by the orange box. If we talk about the infrastructure, and this is also shown by the results, we have to go onto the grid level and also on the community level to better understand the results. So jump onto the next slide, and here we can see the topology and the centralized heat networks of a specific subregion and the impact of the so-called iterative downscaling technique. Here you can see that in the initial condition, we supply more or less the entire subregion, which is one of the marked subregions on the slide before, but we have a little number of connection rate, just 60% or 70% of the connection rate, but we have to improve the connection rate, and this is done and considered by the iterative downscaling technique, which is indicated here. So the iterative downscaling removes specific subregions that are difficult to be supplied from a heat supply perspective. And this results, for example, here in the provision of centralized heat networks in 25 different communities. But we also see that the people that could be connected to the centralized heat networks decreases here, for example, by almost 40%, which means, for example, in the end, of course, that we remove a specific sustainable alternative to decarbonize the heat supply in these specific regions. But from a perspective of a heat supply company, we improve the topology and also the efficiency of the centralized heat network. This last slide of my results here indicates the 3 different downscaling techniques and a very important insight that are generated. First, we see that we have to go into a high spatial resolution if we really want to understand centralized heat networks in the future. It is important to go onto the community level or on the distribution grid level to really estimate and give a realistic estimate or projection for centralized heat networks, which is indicated here by the waterfall diagram. We significantly increase the achievable heat density only if we go into the details of the infrastructure on the community level. However, and this is indicated by the pink bar, we see a significant gap of heat density between 2050 and the heat networks today. Of course, as I said, this is driven or mainly achieved by the reduction of heat density on the one hand, but also that we have to bring the centralized heat network to regions that have lower heat densities than today. And this is indicated here by the pink bar, the gap between the heat density of today's centralized heat networks and the projections in the future of representative centralized heat network in Austria. Okay, let's conclude and summarize the findings. First, we found that the brightest perspective, which is included in one of the downscaling techniques of efficient and local utilization of renewable heat sources, implies substantial changes for the further development of district heating networks. For example, here in our case study in Austria, toward 2050. Of course, also the results demonstrate that particularly densely populated areas are still beneficial supply areas for district heating networks and offer adequate heat densities. Nevertheless, and this was shown by the pink bar, most district heating networks in 2050 will not reach the heat density benchmarks of today's networks and have a significant heat density gap. Also, if we go into the detail on the high spatial resolution. However, and this is a very important aspect in this regard, considering the increasing importance of local renewable heat sources feeding into district heating networks, we assume that these centralized networks will become required in the future and crucial. As I said on the beginning in the introduction, that we have also to think about how to unburden the electricity sector as an important cornerstone of a decarbonized society in the future. And we anticipate our work as a starting point for discussion, the role of centralized heat network infrastructure for enabling large-scale, highly efficient and local integration of renewable heat sources such as biomass, waste, hydrogen, of course, ground-sourced heat pumps and geothermal units. At the very end, I want to acknowledge a specific to my collaborators, Daniel Huppmann, Antonia Golab, and Hans Auer. We developed this work during the summer, and also further references, in particular to the open entrance scenarios and findings, can be found here in this reference by Hans Auer et al. Thank you very much.
Thank you, Sebastian. So if there are any questions for Sebastian, you can write them in the chat. And of course, as we're having the communal question session at the end, you can also ask questions at that point. Thank you so much, Sebastian. Okay, so next we have Jakob. Jakob, can you share your screen in your presentation, please?
Yes, I hope you see it.
Yes, I'm not sure we can, and can we also see you? Yes, we can also see you. Yeah, go ahead, Jakob.
Thank you, and thank you for having me presenting this this presentation here, where the whole idea is looking at how we can convert energy modeling results and outputs and inputs from one set of model and fitting it into another model, in this case, energy plan. So the whole objective and idea behind this presentation is that we would like to model different scenarios that the European Commission uses from primes and have been documented in a Clean Planet for All, and use that in our further research and compare them to for instance, smart energy systems, as Henrik presented earlier in the plenary in the morning. And this is crucial for us, both in terms of in different projects where this is key work, both in the Reinvest project and also in the Sentinel project, where we are using these models to be able to say something about the development of the European energy system and how to move on. So I think the purpose of my presentation today is kind of to describe how we did this, but also to see, okay, why is it important for modelers that we talk together and we allow our results and our outputs and inputs to be available in a way that others can understand them and interpret them? Because in the end, I don't think there's a need for one ultimate model. I think that many models can provide different impacts, and there's not you can say a need for having everything being done a single place, and not all models are open in every way. So at least we can provide our assumptions and our inputs and outputs, and doing it here has been both easy in some sense and also been a struggle to be able to take a scenario made in one model and see, well, what happens if we put that into energy plan. So I'll spend most of my time talking about that, and then I will in the end also show some results about, okay, now you have done this and created these reference scenarios in a different model. How have we actually used that in some further results, and we're also working on now. And I have not done this alone. I have done this with a bunch of my colleagues that also mentioned here below. Let's see if I can switch slide. Here we go. So the whole idea and framework for doing this is a decarbonized Europe in 2050. So understanding what potential pathways are there, and there's a lot of research going on, and I probably couldn't even mention all of it, where both on a small scale, but in this context here on a large European scale for us, it's very interesting to see how can we change and how should the European energy system potentially change towards 2050. And for us to do that exercise, it was quite important to have a reference scenario or a place to come from. And here we took offset in the Clean Planet for All scenarios from the European Commission. And these are all done in the primes model, these scenarios here. And the table to the right here shows a number of the different strategy options that the primes model investigates. So there's something where we electrify, and there's a hydrogen focus, and if we do more energy efficiency. And then in our study, we've taken offset in the three to the right, most right. So that's the combination, the combo, which are the most cost-efficient solutions from the left here. And if we want to achieve this 1.5 degree technical solution to that, or a sustainable lifestyle solution to that, where you can say reduce greenhouse gas emissions, or at least the impact from them more radically than in the 2 degree scenarios, which are represented in all the others. Besides these three, we have also a 2015 baseline, and we have a 2050 baseline scenario. And these are also important, you can say, in the replication, because a lot of these combination and one combo scenario in 1.5 tech and 1.5 live represents a lot of investments and a lot of changes, where when we then go on further and make an alternative scenario, for instance, a smart energy system for Europe, then we can focus on starting in one of the baseline scenarios and then comparing them to, well, how does this compare then to a combo or to a 1.5 tech scenario? So by doing this, we can create some baselines and reference points and so on to understand how our scenarios compare against other solutions. So in the way we've done it is kind of an analytical approach to it. So we've decided that we use the Clean Planet for All and as a background report, and the background report as a reference point, and then to transfer simply all the inputs and outputs we can find documented in these documents. And there's also a scientific paper, and everywhere we can kind of gather what this European model is, and then say, okay, not all of these parameters can go into energy plan, and a lot of them maybe can, but are not understood in the same way. So demands are not necessarily disaggregated in the same way. So how can we aggregate them? How do we put them into the right spot? So my next few slides will show you kind of the 4 sectors where we've done this, and then I will kind of show you how we compared them. So the main way we validated in the end, well, is this a good representation of these primes scenarios in energy plan, or have we missed something? Are we missing a demand? Are we missing a understanding? Well, yeah. Then we looked at this primary energy, so the total fuel consumption, and if needed, we had a reference year of 2005 from Eurostat. And it's key to here also mention maybe the difference between the 2 models. So with primes, you have an investment model that invests over a period of time and creates scenarios based on optimization algorithms and identifies certain technology investments and so on. Not necessarily modeled on what doesn't really go in detail into the yearly simulation of how does this energy system operate, whereas an energy plan, and the reason why it could be interesting to transfer these models into energy plan is that energy plan is more detailed in some sector integration and more detailed in the hourly simulation on a yearly level. So the whole idea behind doing this is that we can say something different than the primes models maybe can do towards a decarbonized future. But it requires that we can do the models, you can say, so we can recompare them. So I'm not sure how much sense all this makes, at least from a graphical point of view, but I'm just trying to put some numbers here, and you don't have to take them and read them and say every decimal point and so on, but it's kind of just to illustrate the process of what we had to do. So when you take the heating sector, it was very important for us to identify it, as Henrik also argued for earlier in the morning, to focus on the district heating. So that's an important point, at least in the energy plan, to identify exactly how much district heating, because energy plan is quite good at simulating these utilization of district heating grids. So that was a key point for us, that to identify how much is there actually in all the scenarios. And then we have electricity for heating, which was quite difficult for us to do in this case here because of the way it was reported compared to how it was understood in energy plan, to actually understand where is a heat pump. Is a heat pump in a district heating sector, or is the heat pump in individual heating, was not always clearly identified. So here we had to make some assumptions for how to move on. And then finally, obviously, individual heating from boilers. This is normally quite easy to get because there are fuel consumptions for the individual households and buildings, normally very, very detailed described. So that's kind of what these tables shows, that we have heat demands for boilers excluding the electric heating. Then they had renewables as one sector also, but again, is that renewables in the district heating grid, or is that in the individual heating system? And then we identified the total heat demand. We from that calculated electricity heating, and then from the district heating ones. And as you can see here, district heating is not really something that develops in the Clean Planet for All, but it's actually something that goes down in the scenarios where we would. This is part of the reason why we did this study, is to actually go more detailed into these numbers and see, well, maybe these district heating can play a bigger role, as we already have discussed. And then supply is either from fuel sources or related to the electricity production. So when we model the electricity sector, we looked at the electricity demands based on the different sectors. So in the primes scenario, they take all electricity for households, for industry, for commercial units and so on, and subdivide that. And some are quite easy to get, and some is a little bit harder to get, because they have to be separated out of final energy demands, which are not the same as electricity demands. So a bunch of exercises went into this to figure out these electricity demands, but in the end, we identified for all the scenarios I mentioned before, 15, 20, 50, combo 1.5 tech and 1.5 live, a fixed electricity demand, which is what Energy Plan understand as a combined electricity demand that is what you can call the classical electricity demand, so households, tertiary sector, but not including heating and the electricity for heating or transport or industry. So in these cases, we have that, and then we subdivide it into industry, electricity for industry, transport, electrolysis in these scenarios, and some for flexible electricity demand. So we get a total electricity demand for all the scenarios that we can then put into Energy Plan as a model. And then power production. Here we could take out for most of the cases simply the capacities of renewables power stations, batteries, and hydropower are more or less reported, as you can see here with an example for the power generation capacity for each of the scenario. And then it becomes interesting when you take a model that doesn't simulate anything hourly, like primes, and then go into putting this into an hourly simulated model, whether these time series data and all these assumptions go back and forward. And here you can make different decisions I can come back to in the conclusion. So for the transport sector, we mainly focused on two things. So first of all, what are the fuel for transport? So we had to identify that, both fossil fuels, but also liquid, e-liquids and hydrogen, and then finally electricity for transport, which we did in the previous sector when we looked at the electricity demand. We identified these things. So in the end, you can see we have, for all the scenarios, a fossil fuel consumption, we have a biofuel consumption, we have electrofuel consumption, and then we have electrified transport, which is either dump charge, means you use the electricity at an electricity demand given by a time series, or smart charge, where we can use the electricity more flexibly, depending on charging, driving patterns, and how many cars are parked, and so on, which is something Energy Plan is able to do, and a feature we used in this modeling to show the flexibility of introducing electric vehicles. And finally, of the main sectors that we looked at was the industry sector. So here this was quite complicated for us in the terms of the way the data was reported. I'm trying to show this up here simply by having that a lot of it was based on growth in percentages from based on different baselines. So we had to use Eurostat 2005, as I said, as growth rates and compare the numbers with the numbers reported and try to get an estimate. So for us, this is maybe where some of the differences can be in comparing our results to the model results from the European Commission when you look at the results. And I will just jump to my conclusions if I can close the window down again. Yeah. And so from these different sectors, we get to these final comparisons between the systems. And what you can see here on the primary energy, after what we've done, and this is kind of also an iterative process, we are able to kind of hit a scenario in Energy Plan that is similar to what the primary energy results shown. So as you can see here, there are some uncertainties. Part of it is coal, and these can come down to a little bit, partly the power production, as you can see over here, the power production, where there's a little less in Energy Plan in the baselines compared to what is the case in the references. And this is when you get into these details about having an hourly model simulating an energy system compared to not having an hourly model, there might be more uses of renewables or similar things. So we were happy with them, but of course I don't think it's ever possible to hit them right on the mark unless if you fix everything, and then the purpose is maybe not as great. So finally, just to quickly show two use cases for it. I hope I have time for that. So one thing is that from this baseline 2050, we adjusted it a little bit, but else basically from the work we've done here, we were able to make an alternative scenario for Smart Energy Europe, and we hope to publish the work on that rather soon. And we can also go in and do an economic comparison between them, where we can see, okay, if we take that Smart Energy Europe, how does that compare with the baselines? and with, for instance, the 1.5 tech scenario. And the reason why these are called adjusted and hours is because we have changed the economic database behind them a little bit, so we know all the costs for everything, because that was hard for us to identify. Yes, I think that concludes my presentation. Thank you for listening.
Thank you so much, Jakob. Again, if you have any questions for Jakob, you can ask them in the chat or at the end in the communal question session. Thank you so much, Jakob. Okay, so now we have Mark with the apples and the pears. Mark, the floor is yours, so to speak.
Yes, thank you very much.
Go ahead. You're welcome. Go ahead.
Thank you for the opportunity to present this presentation with the title Apples with Apples and Pears with Pears. Actually, Imperial is based in London, and Cockney slang, as it's a London accent, there apples and pears means actually stairs. But the coincidence is that in Dutch, we actually say if we want to compare apples and oranges, we use apples and pears. So that's why the title is this. And also, energy plan, which was discussed by Jacob in the previous presentation, in Denmark, they use apples and bananas. So it already shows that there's quite a diversity in languages within Europe and expressions. But we actually want to look at the diversity of models within the Sentinel project. So I will present you some insights we have. It's still work in progress on the design of the intercomparison experiments that we made, and also how we store this in the database that will become publicly available. And it all applies to energy models. So something on the background first. So this is work that's being done within the Sentinel project. In this project, we try to develop an energy system modeling platform, and this platform aims to support the EU transition to low carbon energy system. You can find information on the Sentinel project on the right top if you want to know more. One of the tasks of this project is the model intercomparison that's led by Imperial College and Utrecht University. And so we do this together with Gabriel Regioni, Ian Steffel, Stratos Mikropoulos, myself, and Detlef van Vuren. So we are based in Utrecht University in the Environmental Science Department, and we mainly work with the image model. I will tell you something more about that in a few slides later on. Personally, I especially work on assessing the global impact of climate policies from governments, but also climate actions from cities, regions, and businesses. So the aim of the model comparison is that we want to compare variables that are important for the EU transition, and we want to compare these variables from different models. And this is actually to identify the model strengths and weaknesses of these models, of these participants. But even more importantly, it also gives insights into understanding the differences of key drivers and parameter choices and assumptions. So at the end, we hope to get some kind of range of plausible outcomes that could at least give some indication of the uncertainty of different futures that we present, and that are possible for the EU transition to a low carbon economy. So until now, we have included 4 models that are also participants of the Sentinel project. Energy plan, well, you saw everything about it in the previous presentation. It's an optimization model. It simulates the entire energy system, I think mostly in a single geographical entity, and it has hourly simulations within a year. Also, Calliope is an optimization model. It has some kind of it allows an arbitrary spatial and temporal resolution, so it's very flexible. And it's especially focuses on renewables, so it can show different configurations of the energy system. Then Destiny, that's a simulation model. It also has hourly electricity profiles and also includes all the demand sectors which have been actually implemented within the Sentinel project. Then Image, that's a simulation model, an integrated assessment model. So it includes the energy system. It also includes the land use system, but also the interactions with the Earth system. It's actually a global model, and it has 26 large regions, and 2 of those are Western Europe and Central Europe or Central Eastern Europe. So one of the key features of Sentinel project is that we want to use the strengths and weaknesses of the different models, and we want to build this platform and interlink the models. So currently we use Jacob already showed you a lot of the information from the primes model that's included in the Clean Planet for All or 2030 target plan background studies. But we want to use these input assumptions, for example, for the energy demand model or the power sector model. This can also be replaced by, for example, IMETS, which has a full energy system model. But later on, we also want to match the energy demand and power sector models within the project. And also, we have social and environmental models. For example, we could have constraints on the uptake of wind, onshore wind, or other environmental constraints or resource constraints. So in this way, we want to have a flexible platform and link all the different types of models. And of course, for this, we also want to compare the results between the models. Well, the comparison is done by asking all the model teams to implement the same type of scenario. So for this, we are currently using 2 scenarios, neutrality and current trends. So the neutrality scenario is actually representing the Green Deal. So the EU wants to be climate neutral by 2050, and the current trends is the current implemented policy scenario, which is kind of similar to the reference scenario where all current policies are being implemented. On the right, you see the overall target for such a scenario. So in 2050, total greenhouse gas emissions should be around 0. But as many energy or most energy models don't include land use or non-CO2 emissions, we have also given, based on the primes results, emission levels excluding land use or excluding non-CO2 emissions. The same is done for the current trend scenario, and this is then based on the EU reference scenario. Currently 2016, but we might shift to the 2020 reference scenario. So then what we want to do is we want to do this comparison in 3 rounds. We call it experiments. So first we have a free experiment. That's actually we say to the model teams, okay, you probably already have something on the shelf, and current trends and or a neutrality scenario, and only make sure that you meet the overall greenhouse gas emission targets. And this will give us very good insight about the diversity of the models. So in the next experiment, which we call fix experiment, we will at least fix 1 or maybe a few parameters to see how model results behave if these assumptions are being changed. And then in the last round, we want to experiment with more, fixing more parameters such as efficiencies or costs to really show what the impact is of different assumptions. Well, all this is stored in the comparison database. This will become publicly available at some point in time in the project. And in this database, we use the so-called IMC format. This is from the Integrated Assessment Modeling community. And it actually mainly stores annual results. We are also trying to store more intermediate results. That's still being discussed. For now, we store important variables such as final energy consumption, secondary fuel consumption, installed capacities, primary energy consumption, greenhouse gas emissions, and economic indicators. And for each variable, we have specified different aggregation levels of total or per sector, transportation buildings, or per subsector. Within transportation, you can have passenger and freight. And within passenger, you can have road, air, or shipping, and of course also the fuel that's used to produce the energy. Yeah, as I already explained, we are in the middle of the first round, the free experiments. So I will show you the first results. This is work in progress, so please do not cite, but at least it already gives some nice insights. So first, if we look at the current trend scenario to total power generations, actually the share of carriers or a category of carriers for the different models, and also the official model, that what we call, that's either the reference scenario or the target plan or Clean Planet for All. This shows that energy plan already has quite some substantial renewable generation. Calliope is actually very keen on renewables. That's actually by definition, that's the philosophy of the model. IMET still has some fossil, mainly with CCS, a little gas, a little more compared to the Primes model in the 2050 Clean Planet for All study. Well, this is the same picture, only then for the neutrality scenario. Then energy plan is fully renewable in 2050. Calliope also, and IMET, of course, decreases its fossil and installs more other renewables, hydro and solar. And also the EU model has less fossil in 2050. Well, we can compare other types of variables. For example, which is also very interesting, the installed capacity. For example, Calliope has, relative to the other models, very high capacities, but that's actually for two reasons. Their demand is actually almost fixed between now and 2050, so they assume the surface demand, the activity level or the insulation measures, those kind of things are kind of the same as now. Also, the GDP and population don't have any influence on that, and they also have a lot of electrolyzers for hydrogen, renewable hydrogen production. So for this, they need quite some solar and wind. Energy plan is also relatively high, but they assume demand kind of relative the same with some changes to the EU reference scenario, so not to the neutrality scenario. In IMET, actually, demand is endogenous to the model, so both supply and demand react to each other and to the targets that you set. Then if we look at the demand side, we see that total demand is somewhat higher for IMET, because IMET is actually the Western and Central European regions include more countries than only EU 27 and UK, which is included in the other models. But for the power, it's kind of relatively, we see the same picture between all models for 2050. And then we can also look into more detail into the demand sectors. Well, transport, we especially see that IMET has a relatively implements ambitious measures for efficiency measures. And this is actually in the buildings and heating setting done by the Destiny model. So that's things we have to look into more detail, but these are our interesting first insights. In the industry, it's relatively the same. Only Calliope, who has a lot of also fully decarbonized their feedstock, so they have a high energy demand in this sector in 2050. Well, actually, the main conclusion is that, well, the current first results show that there's actually a very diverse results from these models. It's actually very interesting to think about what is causing these differences. And I think it's also important for the EU to have these multi-model assessments, so they could have more futures which all include plausible outcomes. So especially on these plausible outcomes, we need to do some investigations more in the fixed and in-depth experiments. But yeah, so the differences come from either is an optimization model or simulation model, is hourly or annual production, especially electricity, but also the modeling philosophy, like Calliope could become almost 100% renewable by definition. So as I said, this is a work in progress. So one of the things that we need to do is, I think it's very important to especially link the demand link the demand and the supply in the models, that the demand from the demand models is linked to the supply models, and at least those assumptions are the same. So this is done in the next experiments. We will first fix GDP and population, streamline demand, calibrate historical data, and in the next round we also fix other parameters. Well, yeah, if you get excited by this, you can also join the intercomparison with your energy model. If it covers EU and one or more of the energy supply and demand models. And you can compare your model results with our results. For this, then you need to run the two scenarios that I have presented, current trends and neutrality. And you can contact me at m.r.rofsma@uu.nl. But I think this presentation is shared also, so you can find it later. Okay, I think this is the end. Thank you.
Thank you so much, Mark. And the same as with previous presentations, so you can add some questions for Mark in the chat, or you can wait until the end for the communal question sessions. Thank you so much, Mark. And we'll go on then to the next speaker. So for the next session, sorry, I lost my presentation somewhere. Yeah, so next one is Marta. Marta, please go ahead and share your screen and your camera, and the floor is yours.
Great. Can you please confirm that you can see my slides?
Yeah.
Great.
Yeah, we can't see them. Sorry. Yeah, go. We can't see them yet, Marta.
You cannot?
No.
All right. Just give me a minute. Can you see them now?
Yes.
Great.
Perfect. Yes. Thank you.
Hello, everyone, and I would like to start by saying thank you for having me here today. I would like to present on a recent paper that we entitled Solar Photovoltaics is Ready to Power a Sustainable Future. And let me start with some motivation. We are currently witnessing a solar photovoltaic revolution. I'm not sure if most of you have realized, but the technology with the highest installed capacity in the last decade, so between 2009 and 2019, was not gas, hydro, wind, or coal, but it was solar photovoltaics. If we take a look to the figure on the right, and we can see the global electricity generation from different technologies, we can clearly see that coal and gas, nuclear and hydro are producing most of the electricity that we consume today, but also how wind, and in particular solar, is quickly appearing into this system, into this figure representing the global electricity generation. So we are seeing extremely fast changes in terms of solar PV contribution to global electricity generation. But at the same time, most of energy system, or most of future energy scenarios have underestimated the potential role of solar PV. So a few colleagues, experts in solar PV, gathered together last year and tried to understand what was behind this. And we wrote this perspective paper discussing, well, what is causing this underestimation in models, and what are the potentials for solar PV. And this is what I would like to present today. I have structured the presentation as follows. So I would like to discuss briefly how is it that solar PV gets so cheap so fast, and so enable the fast ramping up of the technology. Do we expect that the cost reduction will continue? Then do we see any possible limitation for large deployment of solar PV in terms of material limitation, land use, or grid integration of large shares of solar PV? And then I would like to have devote some minutes to discuss why many future scenarios have underestimated solar PV, which is strongly related to the previous presentation. So let's start with the first question. How did solar PV get so cheap so fast? Well, first thing that we know is that solar PV has shown extremely fast cost reduction with a landing rate of 26%. So every time that the technology, the cumulative capacity doubles, the cost of the technology reduces by 23% if we look at the whole year, and even lately that's accelerating at 40%. So the learning has been extremely fast. We know that there are technical improvements, efficiency gains, larger wafers, etc. But we also know that there are high-level mechanisms. So we have learned, the technology has learned by producing more and more watts of the same technology, by researching, and also by economies of scale when solar PV start to be manufactured at a larger scale, mostly in Asian countries. It's also interesting to realize that it has been policies that have stimulated market growth for instance, feed-in tariffs, what enable the learning of the technology at the initial states when it was expensive. So we should acknowledge that this is one success of policy. The fact that we have so cheap PV technology today is a consequence of having had it supporting policies in the past. In particular, for solar, we can realize that this is a main characteristic, and it's that solar is a granular technology. That means that when one wants to manufacture a rooftop or to install a rooftop system, well, one needs to use a few solar PV modules, but to install the largest existing solar PV installation with 2.2 gigawatts, then we're using exactly the same PV model, just that we use millions of them. And it's this capability, this modularity, what enables a fast learning. There's existing literature that proves that the lowest the size of the unit, the highest the learning rate. And that's also an indication of what technologies do we expect that are able to learn fast and reduce cost fast in the future. All right, but what about the solar case? Do we expect that cost reduction could continue in the future? It's difficult to predict this, but it's also important to realize there are still many innovations in the pipeline. We have had a sustained increase in efficiency. What's going to happen in the future? As I mentioned, there are innovations in the pipelines. One of them are tandem solar cells. The main idea is that we combine different subcells, each of them transforming into electricity one part of the spectrum, and by doing that, we can attain higher efficiencies. Another innovation is bifacial solar cells, which are able to transform into electricity light impinging on the front side, but also light impinging on the rear sides of the solar cells. And by doing that, they also attain higher efficiency. And we also have innovation in the system level. The fact that now we have very low cost solar cell is enable new configuration, in which we are not that much trying to maximize the generation of electricity, but we want to make a dual use of infrastructure. One example is building integration of solar PV. Another one, as you can see in the picture, could be, or what they are doing in India is covering irrigation channels with solar PV. So electricity is produced, and at the same time, water evaporation from those irrigation channels is reduced. So if we know that solar has been rising really fast, do we have any strong limitations that prevent a massive expansion? Let's try to review them shortly. So first, we could consider material limitation. But to do that, we need to realize that silicon solar cells represent today 95% of the installed capacity, and silicon is one of the most abundant materials on Earth. So mainly silicon is produced out of silica or sun. One material that is typically mentioned as a possible limitation is silver. Silver is used to manufacture these front contract grids, and it's currently represent the consumption of silver in PV industry represents around 10% of the world consumption of silver. So it could be a potential problem, but it's important to realize two things. First, as the technology has learned, also the consumption of silver has reduced, and today is much lower than it was 15 years ago. Also, if needed, silver could be substituted by a different metal, such as copper or aluminum. So from the material point of view, we don't see a major impediment to have a massive deployment of solar PV. What about the land use? Well, first thing I would like to mention is that if we make a calculation, supplying the current global electricity demand using PV requires covering 0.3% of the world land. So of course, we can use the world's land to do that. So from a global perspective, that's not a limitation, but concentrated deployment of solar PV could trigger social acceptance issues. What are the strategies to deal with them? Well, we can try to maximize rooftop PV, although we realize that this would not be enough to reduce temperature increase to 1.5 degrees. So we're also going to need ground mount installation. We could also try to make sure that local communities get also the benefits and not only the drawbacks of new infrastructure. And for this, solar PV and again modularity is ideal because we can share the installation and have energy communities. What else we can do? Well, now that PV is cheap, we can consider configuration with higher social acceptance. For instance, this example of agrivoltaics, where solar cells are combined with agricultural land, and there are synergies that benefits both the production of electricity and the crop yields. Let me now review the first challenge, the grid integration. I have included here different challenges at different timescales, from interannual and time and minutes of subseconds. I won't go, for the sake of time, I won't go into all the details. This has been one of the things discussed during this conference, but I want to particularly reflect on this challenge of variation in seasonal, so having a higher generation in summer than in winter. This is a real challenge, but it's also, it's only extremely important for northern latitude. We should reflect that today, most of the world population and most of the areas where energy demand is expected to increase are located very close to the equator. And in this region, the seasonal challenge is not as significant as it would be in Northern Europe. Great, so now that I have reviewed the three challenges or the three potential limitations in terms of materials, land availability, and grid integration, I would like to go one step further and discuss why it is that the different future energy scenarios produced with different energy models indicate very different penetration of solar photovoltaics. To do that, in the paper we prepared this figure. We plot here a lot of different energy scenarios, and we plot them in the x-axis. We indicate the solar penetration, so the percentage of electricity supplied with solar PV, and in the y-axis, the percentage of electricity demand supplied with wind. And some of these models include sector coupling, so they are using the electricity also to supply heating and transport, for instance. So this means that any point on top of this orange line will be attaining a 100% wind and solar electricity. What is what we see? Well, mainly we see different clusters of models. First, we see all these gray squares that corresponds are all the values included in the IPCC 5th assessment report. Most of them have been produced with integrated assessment models, and they include, as you see, a low wind and solar penetration. And then we are seeing other models we tend to approach more to the orange line, to higher penetration on wind and solar. Most of them have been attained with energy system models. Well, why is that, or what are the reasons that we identify? We need to reflect on the origin of these different kind of models. On the one hand, integrated assessment models started from a global economic model that included several regions, sectors, and decades, but they are typically using low time resolution, so annual values, and low spatial resolution, so one node per country, or most of the time one node per region, per Europe, per America, etc. And then they don't include the network modeling, which means that they are not modeling the possibility of balancing renewable fluctuation by regional integration. Then on the other hand, we have energy system models that started from modeling a detailed modeling of the power system, and that some of them include an interrupted hourly time step and high spatial resolution. So they are modeling the network as the one shown here. But some of them are limited to a smaller region like Europe, and only recently they have started to add heating, transport, industry, or other sectors. What is the main problem here? Well, the main issue is that if some models do not include a proper network modeling or hourly resolution, how do they account for the necessary investment to balance wind and solar? Well, most of the time, to compensate those limitations, they include either an integration cost that is typically high, or they limit the percentage of wind and solar that can provide electricity. And as a consequence, they obtain that most of them, the solar and wind penetration is relatively low compared to what could be attained with a more detailed modeling. Notice that this is also the case for all the primes scenarios that Jacob was presenting a couple of presentations ago. All of them are included here and include solar penetration below 20%. So as a summary, if I will have to answer this question of why it is that PV has been underestimated by many future energy scenarios, the first reason would be that when we have a poor modeling of balancing, so the model includes low time resolution, do not model the network, or do not properly model sector coupling. and add additional costs to account for the balancing, well, this is penalizing wind and solar penetration, and we should be extremely aware of what is a consequence of the limitation of the model, and what is a real solution obtained by the model. There's a second reason that some others have discussed, and it has to do with the use of out-of-date exogenous cost assumption that has missed the fast cost evolution of solar PV. For instance, just to give you one example, see all the cost evolution of different integrated assessment models assumed from now to 2050. So in most cases higher than €1 per watt peak, and see the existing price of solar PV today reaching in average around €1 per watt peak, and in some cases even below. So when we have future energy costs included in the models that are higher than the cost achieved by a technology today, of course, that is penalizing a technology. And now getting to my conclusion slides, I think it's really important that we realize that solar is a reality today, and high penetration of solar, high shares of demand covered by solar are already being attained in different countries. See, for instance, here the different penetration of solar in different regions. What was the situation in 2010? So we had no single country or major region in which solar provided more than 3%. But in 2019, we already have a few countries in which that is attained. We have Germany at almost 10%. We have Italy, Japan. We have California providing 20% of its local demand with solar PV. And we have several European countries and other countries have plans for higher deployment of solar. So we should acknowledge that this is a reality. And I would like to say that in conclusion, of what we discussed in the paper is that the solar PV is ready. The potential to mitigate climate change already now, so in the next decade, is there. And this is going to be key to remain in a path compatible with Paris Agreement, whatever we can do in the next decade. So we need to make sure that our models are good enough and to represent that potential large contribution from solar PV to future sustainable scenarios. Thank you for your attention, and I hope I'm not very bad in time.
No, that was good. Thank you so much, Marta, for your presentation. And as always, you can add questions for Marta in the chat or at the end in the communal question session. Thank you so much, Marta. Okay, and so as the last presenter for our session today is Dieter from Siemens. Dieter, please feel free to start your presentation. The floor is yours.
You can see it already now, or is it?
Yes,
okay,
we can see your presentation.
Okay.
Yeah,
Welcome.
go ahead.
Hello, hi, I'm Dieter Most from Siemens AG. I will present today some results or some modeling we did in the Plan for West project the last 3.5 years. This work I'm presenting here is comprising more models of 3 other partners like Siemens, like Aachen, RWTH Aachen, and the SUS Institute of Berlin. Main contributors have been Lothar Wirber from Aachen and Inchi Yüksel Erwin from the SUS Institute in Berlin. And I will present today what we did here. Let's go. Okay. We did a case study, multimodal European energy concept for achieving CO2 emission reduction goals, and we focused on sector coupling, not modeling only electricity, but also heating, cooling, mobility, and fuels and gas. And this was an annual high resolution of hourly load profiles and along the pathway. And so I had to get also transportation of electricity and grid into our considerations and to see what's happening. And we have a report there, it's 190 pages, where we have all the details inside. It hopefully is published in December now for everybody. And we have a lot of other things where we presented our Plan for West project. I did all the modeling out around this case study. That's why I have 3 case studies in all, but we are focusing now on this case study, multimodal European energy concepts. And Sandrine Charoussi will also present in the plenary panel 3 about the Plan for West project. What have we done in this case study? We made a multimodal operation investment trajectory along the pathway 2020 to 2050. And as it said, multimodal. This means that we have heating, cooling, electricity, transport and all these sectors inside, also some industry sectors. And we're not saying, okay, we have this demand of oil and this demand of coal for heating houses, for example, but we need a thermal energy for heating the house, and then the optimizer we're using can supply with a cost-effective technology. You can choose which technology he uses for supplying this energy, and then we're modeling this. And we've done this with a linear optimization with perfect foresight, and this is very large, and we have some computational problems here. So we have a core spatial resolution. We've modeled whole of Europe, but on a country level, and we have done this here. Then we have disaggregated it to a multi-energy model from the Aachen, RWTH Aachen. We're focusing now on a 2040 year or 2050, whatever we want to focus on, and we're focusing on electricity here. And then we're checking on this disaggregated model what we got from the energy mix from the operation. Is it really feasible on the disaggregation to local postal code numbers here to high spatial resolution? We have a market model inside, and then we can also check the transmission grid operation. Is this feasible, or do we run into some problems for dispatch, redispatch problems, these things, yeah, grid congestion. And what we must not forget is if we talk about multimodal models here, we have power to gas, we have gas demands, we have gas power plants, we have gas for heating. So the gas grid operation has to be taken into account too. And we have to check if the changes in the energy system, and I'm talking about energy system, I mean all, and not only electricity, yeah? If this change in the pan-European energy system is feasible with the gas grid of today, or do we have to run into new issues, new challenges there? This is what we've done here. And then first we started with a multi-model operation investment model. It's a pan-European model. Shortly, what is this? And then some exemplary results. Why do we do this? A European model, all in one, not only countries. We've done this before at Siemens, but we saw that some problems like heating, mobility will be solved on a European level. Yeah, it's not. I can't imagine a world where you have a gas-powered car in France and an e-car in Germany or something like this. And heating is also the same thing. We have it's a global thing because we also have a gas grid, and if we switch to power to heat, then it will be a big problem for the getting all the security of supply in wintertime. And this is a European thing. And we also have the CO2 policies, which are definitely a Euro thing because we have this ETS trading scheme here, and we have the electric cross-border exchange and the gas cross-border exchange, where we have interaction or strong interaction with the other countries. So we have a European energy system to decarbonize and not national only systems here. What we're doing here is we have this multi-model investment model. I want to go into details, but what we get out of this, we get the investment trajectories, the grid we need. We have a cross-border grid, a simplified grid here. We get the electricity generation here on the hourly load profile, and for every year we are modeling from 2020 to 2050. We get the CO2 footprints and the regional price levels, for example, of our commodities, electricity, heating, whatever. And to give you an impression what this means, is very complex. This left side here, this blue one, this is what we do usually for electricity. Yeah, if you do model this. And if you go for a multi-model model, then we have mobility and temperature levels at different temperatures, like low temperature, very high heating, cooling to different levels. And then we can model cooling and heating, and also cooling grids and heating grids, and district heating and savings from building is included. But we also have storages, not only for the electric storages, but also for heating and cooling, cold storages, water storages. We include desalination, which we didn't do here, but we can do it, or gas storages. And we have also to consider about industrial demands, or power to gas, and new ways to provide our feedstock, for example, for chemical industry. And this is what we can do, what we did in the model here. This was a technology open model where we really had the possibility to let the optimizer decide which way he wants to have the energy system, or which way he wants to do when the investments, to get an optimal energy system fitting all the direct use demands we are giving him. Yeah? What we found, one of the outcomes was that we have really found a small PV potential as a really a trigger. First, we have in the model we included large PV farms, and you can the optimizer is free to include as much or to implement as much large PV farms as you want, because area for large PV plants is enough there. But rooftop PV is limited, and we have estimated a conservative limit using today's modules, using today's rooftop, which is feasible for photovoltaics, facing the right direction, southward something or south eastern west. And we did some modeling with this potential, and then we thought about the future and said, okay, the future we have solar tiles, we have balcony PV, we have higher efficiency, we have these tandem PV cells, and so on. And then we made up a progressive limit where we come up with about 180% of the conservative estimation what we can produce by PV in Europe. And if we do this, something happens to the energy system. Yeah. On the upper level here, you see the energy model which comes out of the conservative limit. On the lower row here, you see the energy system where we can implement more rooftop, small decentral PV. Okay? And what we first of all see in the bulk generation world, I call it here, we're all heading for carbon neutrality. The only change is this potential here. Then we have a way where we go to more and more PV, more and more wind, and we're hitting a limit, and then we are having a rebound of nuclear power, and then it's working. Yeah, so it's coming up with carbon neutrality, but this is a world dominated by large bulk generation units. So what you can see it best, have different ways here, but where you can see best is in the electric storage mix, where you can see the hydropower, that's the light blue one. The dark blue one is batteries from electric vehicles, which can bring some flexibility. And the medium blue ones are large grid-connected lithium-ion batteries needed for stabilization of the grid, for day to nighttime shift, for some backup power, and so on. And only some small decentral home batteries here. But if we increase the limit of small PV potential, I'm not forcing the optimizer to do this. He's choosing it on his own macroeconomic considerations. We have a different view. Yeah, we get more PV. Okay, that's clear because we have more potential here. And then nuclear is phasing totally out. We have very low numbers of backup power here. We have much more installations of PV, that's clear. And the storage world totally changes. It changes from a grid-connected world to a world where we have lots of small home batteries. Yeah, this is something which is linked to the decentral PV generation here. And this means that we have to think about different enhancement or enforcement of the distribution grids, that we have to find aggregation for flexibility potentials to facilitate these from the small batteries and so on. So we are coming in a different world, which I call decentral prosumer. And I won't go too much into detail because I don't have the time. I have another poster. You can have a look here. Yeah, and we can have a look in the report. But what you found here, we did this multimodal modeling, and we can get the investment trajectory and the operation trajectory over the past from 2020 to 2050, and this for multimodal means for all these sectors which are energy relevant. And what we do next now is then, this is on a course level, we pass this energy mix, this capacity mix, and the operation mix to the next step. This is a disaggregated multi-energy model. We're focusing now on 1 year because we want to go for higher spatial resolution, and we focus on electricity. And what we're doing there is we can make a breakdown from these country-related numbers down to our more higher resolution, and this is very important for especially for heating supply, for example, and for meeting cogeneration plants, because this is something which we cannot transport easily, like gas or like electricity. So we have to find a close local correlation here. And this is what we're doing. We're checking if this really is possible. And then we can place all the thermal power plants and the thermal small CHP plants or whatever to where we really need our heating, for example. And the other thing is we have integration of decentral electricity suppliers and consumers. And we are making up local virtual power plants out of it. And then we can we treat them as a more in an easy or simplified way. And we have it's facilitating the integration of these local virtual power plants in the market simulation. We can maximize the own consumption and the market trickle operation. Then we can run a market-driven model with it and get running for grid congestion, all these things we would usually have to do to check if we can really operate this energy system with our grids, electricity grid, for example. And what we also have to consider here is that we need some flexibility compensation, and very important here is this impact of sector coupling, because sector coupling has an inherent flexibility from electric and thermal storages in the market, or simply from shutting down a power to heat unit. And this allows them to facilitate the price incentives. And so you should definitely model sector coupling with your market model. This is some results from the exchange flows, which are resulting now from this market modeling. And what we see is, yeah, it's working, yeah, but we have to do some enforcements, especially after 2040 or 2035. Current plants are running out in 2035. So no further plants existing. This is what you're going on. And then what we get out of this here is we're getting all the operation of the power plants and so on. And then we can go to the next step. We say, okay, we have a model of the gas grid. The power plants are using gas power plants. We have still gas heating and so on. And what is happening here? And what we are using here is a gas network optimization model. How it works is a nutshell. You can visit here. We have a nomination of validation model. It's a physical model. It models a gas network, pipelines, nodes, exit, entries, and active components. We have the scenario, amount of gas flows at the entries and exits is coming basically from the considerations of what we've done in the models before. And we are considering the constraints of mass flow and gas pressure drops and Waymore's equations. Gas pressure can be regulated. And the output is the feasibility of the given scenario. Yeah? What we're doing here in this case study, we checked this with our results here. And then what we see is what we did here was a little bit complicated because we did the proof of concept here, how we can do this. The gas grid and the electric grid are not disconnected. They are highly connected because the gas pollets consume gas, or the household industry is the same. And from the gas powers, the gas supply, in future we'll have power to gas and maybe an in-feed to gas grid. So we have a connection here. And then we search for a method for using this from calculating it. So we selected a restricted region where we network topology can be constructed. Germany, for example, did it and brought it into a pan-European correlation. And then we used the available pan-European supply demand data and high-level gas network topology, replaced it with ENSO-G data. We replaced the ENSO-G data with our results from the disaggregated multi-energy modeling. And we checked it here for limitations for power to gas or for the power to gas feasibilities, and if the gas grid is feasible or where it has to be extended. So this is more or less the last bit of what I have here. The key results, we did this as a proof of concept. We say, okay, we should, if you model the European energy system, you should follow all these ways here. And then I would thank you for the attendance here. Please, if you do for modeling, go for sector coupling, go for the market model. And also don't forget the gas grid model, because this is all interwoven, and you have to respect these feedback loops, and they get different manifestations of your energy systems if you don't do it, yeah? Okay, then I'm finished. Sorry, it's a little bit long time.
Thank you, Dieter. Many thanks for your presentation. So we will now go on to the questions. If anyone has any questions, please feel free to. We've been posing some questions and there are some replies already in the chat. But I would then invite you now from the participants, so the attendees here, if you have any questions for the for our speakers. Okay, it seems like we don't have any questions. I just have one question for Dieter. So Dieter, did you model also the new developments in gas grid, which is of course also somewhat connected to to Power2X, so also to the electricity grid both? So basically the incorporation of hydrogen into the energy system and how that might change, let's say, the gas grid, and as well as some options for basically integration with the power system, with the electricity system.
We had a whole technology set, also including hydrogen gas turbines. We can use hydrogen for fuel cell electric cars. Can also generate a Power2X on hydrogen, or can make from these hydrogen synthetic fuels, which can be burned, for example, in a gas oil burner or gas burner, whatever you have, or in an e-car. And the optimizer is free to choose the technology set he wants. Yeah, and he has to fulfill also the supply chain, the different energy modes there along to fulfill the demand, but he's not choosing hydrogen as a gas turbine plant, for example, but he's choosing some fuel cell electric vehicles in the end. Most is electric cars, but some like 5 to 10% is fuel cell electric cars. Then we need some electrolyzers at the end in 2050.
Okay, so and how do you do the decarbonization of the gas network?
The decarbonization of the gas network, it's interwoven. We have the decarbonization targets, which is in the multi-model investment model. And the decarbonization target is only that we say, okay, we didn't go for decarbonization of this gas grid, but we want to check if we want to go like an infeed from electrolyzers, yeah? Or we have a changed volume flows from the gas power plants, new power plants in different locations. If you can still use the existing gas grid and the current plants to do this, or if we run into some problems. We're not changing the gas grid in its nature.
Okay. All right. Thank you so much, Dieter. So if there are no other further questions in the session, and I think we don't have any further in the chat. Oh, we do have. Yes, go ahead. I think.
Can I just say something, Marianne?
Yes, go ahead, Marianne.
Follow-up question to Sebastian. Sebastian, I was just wondering, were you also comparing where decentralized options would make sense compared to centralized one from a cost optimal perspective, or you assumed all gets centralized? Yeah.
Thank you very much for this question. This is a very important aspect. Maybe I forgot this in my presentation. We downscaled the cost minimal solution of the Genesis mod resource, and this also includes heat sources or heat technologies such as heat pumps, for example. So we just analyzed, let's say, the implications of the heat sources in the cost optimal portfolio, which means we need centralized heat networks. So there's the alternative of heat pumps, for example, are assumed at more rural areas, for example, but in densely populated areas, we see this requirement for centralized heat networks from an efficiency perspective.
And can you come up with some more general recommendations that would also fit other countries that, I don't know, with a population density below that, it's a centralized solution, or does that depend on too many factors that are locally, like the heat source as well? Or could you come up with these recommendations for modelers in general?
Yeah. In general, I would say that so we downscaled the numbers from one single node. So we also did some investigations on a local level where we also analyzed the distribution grid, for example, of the district heating network. So to give a recommendation, I would say if the cost optimal portfolio includes the, heat sources such as, for example, biomass and hydrogen, you have to consider network infrastructure expansion in densely populated areas. And in the end, you have to do this analysis on a highly spatial resolution in the end. So if it's economic viability, if it achieves economic viability or not, is always a specific analysis on a local level. But in the end, we, let's say, recommend to use heat sources such as biomass and in particular hydrogen. If it's part of the game, let's say, then it has to be used in co-firing and centralized heat networks from an efficiency perspective.
Okay, thanks. But there's no number like what below this population density you would go for centralized, and the other, is there some population
Okay, just to name a number in the end, and we used a number of, let's say 150 for the first downscaling technique. But in the end, if you go on a higher spatial resolution, which means on the province level or community level, so 150 is just to get an idea where to downscale the number, and then you have to think about the topology of the network infrastructure. So as I showed in my results, the first downscaling techniques, let's say, assume 150 persons per square kilometer, for example, but then you have to analyze the topology. And this is very important. This also increases the heat density of the centralized heat networks. You need both steps in the end. So this is very important.
Okay, great. Thanks a lot. I might come back to you.
Yeah, thank you very much for your question.
We have a question from Zoran. Hi, Zoran, for Marta. So basically, Zoran is asking, do you think that the solar, electric, and thermal production can cover the hourly winter demand? And if no, how do you suggest we reduce emission from the system? That's Zoran's question.
Thank you for the question. Let me answer this way. All the model results that I was comparing try to answer the question of what is the best combination of technologies to make sure that we can supply electricity, heat, transport demand in winter and in summer, in the morning and in the evening, so through every hour in the year. Of course, what we see when we do this cost optimization is that in countries that are up north, we don't see a high contribution from solar to cover electricity and heating demand in winter. But then we have strategies to make sure that heating and electricity is also covering in winter. One of them is balancing solar with wind, which shows an opposite seasonal variation. But one other is to produce extra electricity in summer using solar, transforming that electricity to things like electrofuels, for instance, hydrogen, and making that hydrogen or using that hydrogen to supply some of the demand in the winter. And I did not imply to say that we only need solar. Of course, we also need, when we look at the zero emission scenarios, wind energy and balancing strategies, including storage, but also interconnection. We need everything. My point is that we are seeing when we include all the flexibility options, we are seeing that solar can play a major and a very large contribution. And we need to make sure that we are that our models are not limiting that contribution, because we want to make sure that the results that we are seeing are actually a result of the model and not a manifestation of the model limitation. That was my point.
Thanks so much.
Thank you. Okay, so maybe we have time for one more question, if there is another question before we finish. So we have 3 minutes left. Well, we're already going beyond, but at least we can do until 3:40. Yeah, I think maybe so. There are no further questions. So all that's left is to thank the speakers and thank the attendees for being here and for your interesting questions. And yeah, do enjoy the rest of the. I hope you enjoyed the rest of the conference. And thank you so much for your time. Thank you.
Thank you.
Bye-bye. Bye.
Thank you.
Bye.